So now we can better understand precipitation reactions. In 1A, we learned to predict what things will form a precipitate, but we were looking at the solubility table, and we basically said this is either soluble or insoluble. Now we recognize that there's actually a range, right? So we're going to use that reaction quotient to help us to predict, is something going to precipitate or not? So remember that KSP is the value of the solubility product constant at equilibrium only. It only applies at equilibrium. We can calculate Q. It's calculated using the same equation, but it's calculated with the current concentrations, and it can be calculated at any sort of conditions. And then to predict what's going to happen in terms of the reaction, we compare Q to KSP. Q can be different. KSP is always going to be the same at a given temperature. So if I calculate Q here, and this value is smaller than the KSP, that means that the equilibrium or the reaction is going to proceed in a way to move Q towards KSP. It will keep moving until Q is the same as KSP. So if Q is too small, I need to increase these concentrations in order for it to be equal to KSP. So if Q is less than KSP, that means the solution is unsaturated and more of the solid can dissolve. If Q is equal to KSP, the solution is saturated, it's at equilibrium. If you add additional solid, it will not dissolve. A solution in which you have solid in equilibrium with the solution above is not a supersaturated solution. Okay, that's a saturated solution. A supersaturated solution is when you have more dissolved in solution than can be in solution. And that is an unstable situation, and usually the solid will precipitate out of solution. Sometimes it's not aware that it should precipitate, and so it needs a bump or something before it'll precipitate. So we can use Q to predict whether a precipitation reaction will occur when two solutions are mixed. So we need to identify the potential precipitate and calculate Q and compare it to KSP for that potential precipitate. If Q is larger than KSP, then we anticipate that precipitation will occur. Let's do an example. A solution containing lead-2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.0600 molar in lead nitrate and 0.0158 molar in sodium bromide. Does a precipitate form in the newly mixed solution? So we'll do the same thing we did in Chem 1A. We'll look at the reactants and predict what the products are. So we have lead nitrate, and it's lead-2 nitrate, and we're mixing that with sodium bromide. And so this has lead-2 ions and nitrate ions, and this is sodium ions and bromide ions. And then we're going to swap the partners and see if any chemistry occurs. So we've got lead-2 plus with bromide, and we've got sodium with nitrate. So for those of you who didn't take 1A with me, I think of metal ions as being masculine and non-metals or negative anions as being feminine. And so here we've got a guy and a girl, and they're going to go to this party. And here's another guy and a girl, and they're going to go to the party. They're dissolved in the solution, and they're mixing. And when lead and bromide meet, there could be a chemical reaction. They could really dig each other, right? And so they will get together. They really like each other, and so these are the ones you find in the back porch necking on the couch, right? And they're not in the party anymore. They precipitated out of solution. And sodium and nitrate are like, oh yeah, this is a great party, and they're just having fun. So it always has to be a positive and a negative, and the positive ion's always written first, just out of convention, like formal invitations are Mr. and Mrs., just because that's what everybody does. So we're going to look at these two, and in Chem 1A we'd look at this and say, well, lead bromide substances are generally soluble except lead 2 is one of the exceptions. And we would predict that this is going to form a precipitate. And we would predict that this is going to be soluble. So we would write the formula for this, which would be PBr2. We'd call it a solid. And then we'd have NaNO3. And that would be aqueous. Then we'd have to balance it. We need 2 of these. And 2 of these. Any questions about that? It should be reviewed. So I'm going to erase what's down here. We don't need that anymore. Now, do you have to write out this whole equation? No, you don't. But you do have to identify what's the thing that might precipitate. If you try to do this calculation with sodium nitrate, you're going to get frustrated. Here we've got a big hint because we're given KSP for KBr2, so that's probably what we need to look at. So then either physically writing it out or doing it in your head, which is maybe a little risky at this point in the semester. Think about, okay, what happens when this dissolves? 2Br minus. And so the solubility product expression there is the lead concentration times the bromide concentration squared. This 2 becomes the exponent. It doesn't show up in here. We don't take the bromide concentration and double it and then stick it in there and square it. Okay? This 2 gets used, but it's only the exponent. Don't stick it inside the brackets. I saw some of that on the exam too. So what we want to do is we want to calculate Q. We know what KSP is. What we want to do is calculate Q. Q is the same expression, but we're going to use the actual concentrations. So what's the concentration of the lead ion in this mixed solution? 0.06. So we got 0.06. And the bromide concentration, we do need to be a little careful because if this was like iron bromide or something where you had more than one bromide, then you'd have to think about, well, we want the bromide concentration. Here, there's 1 mole of bromide for every mole of the compound, and so the bromide concentration is the same as the concentration of the compound. So we're going to put that in there, 0.0158 molar, and that's squared. And then we calculate that. So 0.06 times 0.0158 squared. (1.5 times 10 to the minus 5). So that's Q. How does that compare to KSP, which is 4.67 times 10 to the minus 6? Our Q is larger. It's not kidding. Q is larger than KSP. So, is precipitation going to occur? Yes. Because this reaction is going to shift around to make KSP correct. So these concentrations have to come down in order for Q to get smaller until it reaches the value of KSP. Make sense? So yes, a precipitate will form. So selective precipitation is when we add a reagent that will form a precipitate with one of the ions, but not the others. So selectively precipitating out one kind of ion. And this idea is the basis of this qualitative, sometimes called a qual scheme, where we take these unknown solutions of cations and we try to figure out what's in there. We do that with selective precipitation. So we choose a reagent to precipitate the desired thing, and we choose that based on the KSP values. The difference in KSP values to get one to precipitate and the other not to precipitate, the difference needs to be a factor of at least 1,000, 10 to the 3. And the concentration needed to trigger that precipitation can be predicted by comparing Q and KSP, just like we did. So magnesium and calcium ions present in a solution can be separated by selective precipitation with potassium hydroxide. What minimum hydroxide ion concentration triggers the precipitation of the magnesium ion? And we're giving KSP values for calcium hydroxide and for magnesium hydroxide. So if we look at these KSP values, this is 10 to the minus 13, and this is 10 to the minus 6. So which of these is less soluble? The magnesium. Okay, it has a smaller KSP, it's less soluble. The magnesium is going to precipitate first. The calcium hydroxide, while some of it will precipitate, it's not going to be significant. We probably wouldn't be able to detect it, right? Okay, so we've got magnesium at 0.025 and calcium at 0.011. And we need to know what's the minimum hydroxide ion concentration for there to be precipitation. So let's look at KSP for the thing we're going to precipitate. And we always have to consider the stoichiometry here because that affects the expression. Got magnesium and 2 hydroxide ions. So when we calculate KSP, it's the magnesium ion concentration times the hydroxide ion concentration squared, right? Right at the saturated point, Q will equal KSP. So we can calculate, based on our magnesium concentration, what hydroxide concentration would give us a saturated solution that would fulfill this equilibrium. And the minimum would be just above that. So we know that KSP is 2.06 times 10 to the minus 13. And we've got 0.025 molar of the magnesium. And then we've got the hydroxide ion concentration squared. So the hydroxide ion concentration is going to be the square root of 2.06 times 10 to the minus 13 divided by 0.025. I'm getting 2.87 times 7 minus 6 molar. So if I want to precipitate the magnesium, I want to use a concentration of hydroxide that's higher than that. Make sense? You guys are way too quiet. Finding the concentrations of ions left in solution after selective precipitation. The solution is 0.085 molar in lead 2 and 0.025 molar in silver. If selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? What is the concentration of each ion left in solution at the point where the second ion begins to precipitate? Well, let's tackle these one at a time. What's going to precipitate first? We're going to look at our KSP values, right? This is 10 to the minus 5, that's 10 to the minus 10. The silver chloride is going to precipitate first. So silver chloride, we got silver ions and chloride ions. KSP is the silver ion concentration times the chloride ion concentration, and that is equal to 1.77 times 10 to the minus 10. So it's asking what is the minimum concentration of sodium chloride to precipitate this silver, to begin the precipitation. So we've got the silver ion concentration. We're going to plug that in, and we're going to solve for the chloride ion concentration. So we've got 0.025 times the chloride ion concentration is equal to that KSP. Yeah, 1.77 times 10 to the minus 10 divided by 0.025. .08 times 10 to the minus 9. So as we're adding sodium chloride, when we get to this concentration, the silver ion will begin to precipitate, right? So that's the answer to A. Then the question is, what's the concentration of each ion left in solution at the point where the second ion begins to precipitate? Well, what concentration of chloride is needed for the second one to precipitate? The second one, I'm going to do this in blue. The other thing we've got going on here is lead 2 chloride. So that's giving us lead 2 ions and 2 chloride ions. KSP for that is equal to the lead concentration times the chloride ion concentration squared. So to calculate the sodium chloride concentration where the second ion begins to precipitate, we have to plug our lead concentration in here and solve for chloride. So this is equal to 1.17 times 10 to the minus 5. So the chloride ion concentration, because that's squared, it's going to be the square root of KSP divided by the lead concentration, 0.085. I'm getting 1.17 times 10 to the minus 2. Anybody else get that? Okay. So this is the chloride ion concentration when the lead begins to precipitate. So at that point, what is the lead concentration? Not meant to be a trick question, but it kind of is a trick question. It's 0.085, right? Nothing's really happened yet. So the lead is just going to start precipitating, so it's still 0.085 molar. What's the concentration of the silver? This is the concentration of chloride. We plug this chloride ion concentration in over here and calculate the silver ion concentration. That's the concentration of silver that's left in solution, the rest of it precipitated. That make sense? Yes.
So the first reaction with the silver chloride, it all did precipitate out.
No.
So as you keep adding more NaCl, will it
It'll continue to precipitate.
along with the lead as well?
Okay, so we're back after our issue with Wi-Fi. And I'm writing on the screen and nothing's showing up. This does not bode well. Yeah.